If we consider the last class as a class number 15, this is class 16 of this course CH576. Okay. So today we are going to start what is known as system of interacting particles. So far we have dealt with systems where particles don't interact, isn't it? Uh, they are non-interacting or weakly interacting. There's like ideal gas, maybe classical ideal gas, like Maxwell-Boltzmann gas, or quantum ideal gas like Bose-Einstein gas or Fermi-Dirac gas. Uh, Also, we have done something like non-interacting collection of harmonic oscillators, uh, collection of rigid rotors, isn't it? And you deal with rotational and vibration and rotational partition functions. Okay, so today we will start what is known as interacting particles, but again, you'll see that um, we'll not really deal with interactions. We'll do something, we'll skip that, and, but that will be revealed as I progress. Uh, so let us start with this. This everybody knows about it. This is uh, lattice vibrations and normal modes. How many of you know this? I am sure some of you had a course on solid state physics or chemistry, isn't it? Hmm? So how many of you had a course on solid state physics? Can you tell me? Can you unmute yourself and tell? One of you. I hope you are there.
Yes, sir.
Yeah. So how many of you had this exposure to solid state chemistry, for example? How many of you had taken solid state at any level, like even class 12 is fine? Solids.
Yes, sir. Please lecture.
Okay, some of you must have. So it was even people who are doing master, they must have had it in their BSc, isn't it? Kailash Shahu, Ajit, you guys had
Yes, sir.
some solid state, no?
Yeah,
So why you are not answering? I'm asking the question. No? So
but note these topics what you wrote.
okay. Anyway, so we'll talk about it a little bit now. So basically, solid is made of what? So I can think of simple thing made of atoms, and you know that they are sitting on a specified location. You know that, and they form what is known as lattice, isn't it? The crystal is actually that you have sites periodically arranged, and on those sites you have atoms sitting. Okay, for example, say if I go to copper or any other metal or even a salt like sodium chloride, potassium chloride, we'll have sites where potassium and chloride they're sitting, isn't it? And their particular arrangement. I'm not going into that details. Different kind of arrangements. We'll not talk about it much now. But the idea is that you have a arrangement on a lattice, and these atoms or ions, whatever, they interact, isn't it? In NaCl, this Na and Cl they interact, of course. So they're interacting particles. Okay. Uh, for example, even forget about sodium chloride. If I take argon, for example, argon gas, I can actually even solidify argon. It is possible. Even better than this is nitrogen. So if I take nitrogen gas, I can solidify. I can form solid nitrogen, for example. So in order to go from the gas to liquid to solid, what is important, you know, that your particles or the entities, for example, molecules or atoms, which the substance is made of, uh, they should be interacting, isn't it? They should interact. Without interaction, there is no phase transition. There is no transition from gas to liquid to solid. And you know all this because Ideal gas, there is no interaction between this between the constituents of ideal gas, and as a result, you don't see any phase transition, isn't it? There is no transition between from gas to liquid to solid. So you have to have intermolecular interactions, isn't it? So we have solid is an example where the particles, atoms, or ions, whatever you to call it, and they interact. They have interaction. So it's an example of systems, of a system of interacting particles. Okay. So I can think of, let us start. I have say, as I usually do. Uh, so you have say solid. I'm considering, and this is made of n atoms, n number of atoms. N is very large. If I take a piece of solid, n is huge, of course. And each atom I can describe with some position coordinate. Uh, by its mass and position coordinate. Okay. So now, for example, say ith atom. I have ith atom. The mass of that atom is mi. Okay. And the position is ri. Now ri means what? It will have three components, x, y, z. Is this clear? But rather than calling it x, y, z, I'm just using different notation. I'm calling it x1, xi1, i2, xi3. It is like xi, yi, z or zi. Okay. Is this clear?
Yes,
This is the
sir.
notation I'm using. That doesn't matter, just because the book I took, they're using this notation. And think about it, that each atom has some equilibrium position. No, it is what happens in solid. You know that they don't translate much. They vibrate around its lattice position, isn't it? Equilibrium position. So the equilibrium position, and around which it will vibrate. It will have small amplitude vibration in solid. That is what is happening. So I can always define, for example, to describe the displacement, describe or measure the displacement from the equilibrium we introduce some uh, variable into the variable. The variable I'm calling it xi, which is I alpha. And you can tell me what is this? This is nothing but x I alpha minus x I alpha 0. You understand, no? This is equilibrium. If you have harmonic oscillator, you know x minus x0, that x0. So this is a displacement. So it is the displacement related to equilibrium position. And of course, x, the notation I'm using, this x stands for xyz. If it is x1, then it is x. If it is x2, it is y. And if it is x3, it is z. So basically, what are the values of alpha possible? So this is for the ith particle or
1,
ith
2, 3.
atom. 1, 2, 3. Is this fine? Is this fine?
Yes, sir.
So then the kinetic energy of vibration of the solid, what should be the kinetic energy? This is kinetic energy notation, huh? You know half mv square, no? Kinetic energy is half mv square. Everybody
Yes.
knows. But how many atoms are there? n atoms, but each atom has three direction, no? X, Y, Z, like x1, x2, x3. I'm telling, no? So actually, what I'm going to get, I'm going to get half. I'll have two sums. I hope you understand. mv square. So I assume that all the atoms have same mass. I can assume also, I can assume they have different mass. So I put mi. Okay, make it more general. And then what should I do? I should
XIL
do,
product square.
yeah, I should actually write like this. X, because this is your notation, no? Xi alpha dot, this dot, huh? Square. Is this clear? If I write like this, and your alpha should go from 1 to where to where? 1 to 3, and then I should go from 1 to capital N. Is this clear?
Yes, sir.
Okay. This is kinetic energy. But again, I know that if you look into this expression, x is xi plus x0. X0 is constant. So this can also be expressed in terms of this variable xi, isn't it? What will be the answer?
XI alpha dot square.
Okay, is this clear? Because if I take derivative of this, 0 is 0, like x0 is 0, is a constant with respect to time. Is this clear?
Yes.
So in other words, this is, if I write xi alpha, this is the alpha component of velocity of ith atom. Is this clear? This is exactly what I put here. So we got kinetic energy. I hope this is fine.
Yes, sir.
Very easy. The kinetic energy of vibration. Because you see, equipartition theorem what says that each degree of freedom will contribute half kBt. So kinetic energy will contribute how much? Half kBt in three directions, 3 by 2 kBt, isn't it? And then I will have a left with vibration, not vibration, sorry, potential energy. This potential energy will also contribute half kBt in one direction, in three direction, 3 by 2 kBt. So half, so 3 by 2 kBt contribution come from there, 3 by 2 from here. So adding these two, you'll get 3 kBt, and then multiply the number of particles. So you'll get 3n kBt. What is that? That is your internal energy. That is your equipartition, isn't it? And if I take a derivative with respect to temperature of that quantity, what I'm going to get?
Heat capacity.
Capacity.
Heat capacity. And what is the heat capacity? 3n kb, isn't it?
Yes, sir.
And what is this now known as? This is known as Dulong and Petit's law. I think you guys should know, isn't it? This is how it comes. The
Yes,
physics
sir.
is like that. Okay, so now the next thing would be to introduce potential energy. So let us do potential energy thing. You have a class after this, all of you? Many are having, or you have class, someone has class. Okay. So the potential energy are calling it V, capital V, and it is a function of what? All the coordinates, no? Isn't it? But I can always say this is a function of like x, uh, one, whatever. Okay, this is in general potential energy, and this can be expressed as a Taylor series. When you can express this as a Taylor series, when you have displacement which are small. So what is happening physically? Physically, I am looking at, for example, I can think that these atoms are connected by some spring, no, on the lattice. You understand, no? And because of this spring, you have this whatever the spring has some. So because of this spring, you have some potential energy. So 1 is connected to 2, 2 is connected to 3, like this, isn't it? Okay, so this is how the kinetic energy sums comes. And if I assume that the displacement, the relative displacement or displacement of each particle from its equilibrium position is small, then I can express this kinetic energy, not the kinetic energy, potential energy, as a Taylor expansion, as a Taylor series. This is because since the displacement are small, try to visualize. Okay, try to visualize. You have a lattice. Each lattice side has some atom sitting there. They are interacting through each other. Also, they have their own kinetic energy, and also they have interaction energy between them, isn't it? You understand what I'm saying?
Yes.
Yes. So now let us write down the, because of that you have potential energy. Let us explain the express the potential energy in as follows. Your V is something like V0. V0 is the potential energy of the system when the particles, all the atoms are in their equilibrium positions. Okay? And then it will vibrate a little from their equilibrium position. But the vibration is small, so that the displacement from the equilibrium position is little. So then there will be correction over this potential energy, isn't it? And that you express as a Taylor expansion. So you'll have extra terms. This is coming because all these atoms they are moving a little bit, they're vibrating a little bit from its equilibrium position. Is this clear? But they are interacting with each other. They are
Yes.
interacting with each other. Remember, because of that they are stable. Okay, because of that they are stable. So, so this is how this is V naught, and then you'll have uh, you have to take a derivative of this V with respect to what? Can anyone tell me? It has to be V x I alpha, but this has to be taken at the equilibrium position 0, and then I multiplied with the relative displacement. No, what is that?
Xi alpha.
Xi.
I alpha. Is this clear? Why do I put sum outside? Because I have to take this in 3 direction and I have to take this for all the atoms, isn't it? So I can put I and alpha. You understand, na? I'm just collectively putting it like this. I can put another sum. You understand now what is there? I have to take a sum over alpha I, which runs from 1 to 3, 1 to 3, and alpha, which runs from, sorry, alpha runs from 1 to 3, and I runs from 1 to n. Is this clear? So take this sum for each atom, and for each atom there are 3 directions. What is the second term? You know, half second derivative, isn't it?
Yes.
Now you have to learn this, because when you take second derivative, you have to essentially, I could have put d2v dx I alpha square or dx I alpha 2. No, there's a way of writing, because there will be non-diagonal terms, off diagonal terms. So this is how it is. Similarly, I could have written xi I alpha whole square. No, it should be xi I alpha times xi j gamma, and you have to sum over ij alpha gamma. Is this clear? Is this clear what I have said? You understand, no, what I am saying? Because I cannot write only square there, because there will be off diagonal terms. Because if I displace one of the particles or the atoms in y direction, you can also have 2 other directions, the x and z. So I can, but I can pull it in the x direction, y direction, and see the effect in x or other 2 direction, y or z direction. So it can have off diagonal terms. It will have off diagonal terms in general. Okay, and then higher other terms which I am not writing. Is this clear? This Taylor expansion.
Yes, sir.
All these are evaluated at the equilibrium position. evaluated as okay, so that your x I alpha is actually x I alpha 0. Okay, is this clear?
Yes, sir.
I or j from, let me write down, 1 to n, alpha or gamma from 1 to 3. Okay, in unit of 1. Okay, is this clear? This is exactly what it is. And V0 is your potential energy in equilibrium position, no? Okay, fine.
Yes, sir.
Now what about this term?
Zero.
Why it is 0? You know this is 0. All of you know it is 0. Why it is 0? Because you are at the minima of a potential, no? So derivative of that minima with respect to any, if you go in any direction, is going to increase the potential energy. So it is 0. Is this clear?
Yes, sir.
What about this guy? Second derivative?
Greater than 0. It would be greater than 0.
You don't know that actually. It
So
is,
we are at minima. So second
if you are
derivative would be
starting at the minima, it is 0. But yes, usually it is greater than 0. But this is called Hessian actually. It is greater than 0 because if you start at minima and you displace the particle a little and see the second order correction, it is greater than 0 because your energy is increasing any direction you go. But in, if you go to another, if you don't start at the minima, you start at the barrier top somewhere, not here in this case. But this quantity could be negative, isn't it?
yes.
This, but this quantity is always 0, whether it's a minima or a maxima. So this quantity actually gives you is nothing but the curvature. Just think carefully. So what I'm going to do, I'm going to now write down this potential energy in a slightly better manner. So I'll call it V equals to V naught. This first part is 0 plus half sum over I alpha j gamma whatever. And this thing I don't want to write again and again. I just write as something like A I alpha j gamma xi I alpha j gamma. Is this clear? This is how I am writing. What is A? This is A. This is your A. This one is your A. The one I just written. This I am calling A I alpha comma j gamma. Some coefficient. So this is quite complicated, the potential energy part. So what is the Hamiltonian then? Total Hamiltonian. You have kinetic energy. Kinetic energy, you remember, it is there in the other slide. It has to be mi, not alpha, mi. Oh, sorry. Mi this one plus but do you see one thing here? What is you should see? You should see that because of the potential energy part, I have problem. So my problem What are the problem I have is because of the potential energy part. Look at it very carefully. Why?
Coupled. Yes.
Why? Because you see these coefficients are non-zero, no? And it actually couples xi I alpha with xi j gamma, isn't it? So it actually couples x with y, y with z, x with z of different particles, all different atoms, isn't it? Can you see that?
Yes, sir.
Yes, sir.
Because of this term interacting, no? Okay. So what should I do? So now this Hamiltonian, with this Hamiltonian I have problem doing this. Very complicated Hamiltonian actually, in general. What should I do? Any suggestion? Any suggestion? What should I do?
We can make a neighbor group approach.
No, it is you can do, but actually there is one way out, and that is done in classical mechanics. You guys would not know. So actually, I can make a transformation. I can change my coordinate system. So I go from this coordinate system to another coordinate system where this coupling is gone, where these vibrations, this potentiality of vibrations, all are, you understand, no? All are decoupled. You understand what I'm saying?
Yes, sir.
So what I do, I do a change of variables. So we had variables like I alpha. From here, we go to another something qr. Of course, 3n is the number. Such, but in such a way, this is called generalized coordinate. And in this coordinate system, so basically, I'm changing this coordinate system. Okay, and this change of variable eliminates the cross terms in the potential energy. And I'm not going to do it, but you have to trust me that this can be done. And if you want to know more about it, read some classical mechanics book. In quantum mechanics, chemists, they also do this. You know, some kind of unitary transformation you do sometimes, isn't it? Basically, you're given a matrix which has off diagonal terms, and then you make some transformation, multiply that matrix from left and right by two other matrices, so that you get a matrix where these off diagonal terms are gone. Only the diagonal terms are there. Remember?
Similarity transformations.
What is that?
Similarity
Similar
transformation.
transformation, yes. So it is something like similar, it is like similar transformation. So changing your coordinate system, going from one coordinate system to another coordinate system. But this is we're doing in classical mechanics. So what is classical mechanics? Basically, what you do, you express this old variable as a linear combination of some new variable. Something similar I did in CH425. If you go and check your notes, but in the context of classical quantum mechanics. So basically, a proper choice of coefficient will give you this. You understand?
Yes,
Basically,
sir.
this coefficient, you say a proper choice of coefficients uh, gives the following Hamiltonian. Now, can you tell me what will be the Hamiltonian in this new coordinate system, QR? this generalized coordinate. Hamiltonian, can you tell me? Of course, you can tell me. H is V0 is V0, no? It was there.
Yes.
I had forgotten to write V0, so there will be V0 here. V0 plus this. Okay. What else?
Kinetic energy.
Kinetic energy and potential energy. So your kinetic energy is going to be this transformation is such that each of these generalized coordinate would have same mass. There will be no mi like this. You understand? So you'll have something like this kinetic energy. What is potential energy? You're going to get half okay, as if your mass is unity. Can you see this? Of course, this omega r squares are positive constants. Someone's is on actually. Mike. Now this Hamiltonian is familiar to you. I think familiar to everyone. No. What is this Hamiltonian?
Harmonic oscillator.
Yeah, with some constant, no? Plus some constant, isn't it? This is harmonic oscillator. Okay, and this QR, which I'm called generalized coordinates, they're also there's another name to this, and this is more popular. You know this name? These are called normal coordinates. And if you are looking at the vibration in this coordinate, this is called normal mode of vibration. You know from your some spectroscopy class or from some course, you should know, isn't it?
Yes, sir.
So in normal coordinates, so each coordinate vibrates independently of each other, and they're harmonic and independent. Is this clear?
Yes.
Now basically this part is like this part is a harmonic oscillator kind of. This is harmonic oscillator Hamiltonian, isn't it? It's like half the one which is inside the sum. And you know the quantum mechanics of it, isn't it? You can do the quantum mechanics. Now I can do quantum mechanics here. If I do quantum mechanics, I'll get energies. What are the energies? This is the energy for one of the normal modes. Huh? And this is going to be, you know, some quantum number, NR I'm calling it.
Plus half h nu.
Is fine? H cross omega,
Yes,
I'm
sir.
writing in terms of omega. Is fine? So in general, the expression, the energy I can write, the energy is going to depend on many quantum numbers like N1, N3, and isn't it? This is going to be some constant V0, which I'm carrying with, plus sum over R goes from 1 to 3n. Is this clear?
Yes, sir.
And this I'm going to write in a slightly different manner. I'm going to write it something like minus n capital N times something called eta plus I take the half 0 point energy outside, no, half h cross omega r. I can take it outside, isn't it? You understand? Because it does not depend on nr. Okay, so you understand what I'm saying? It does not depend on nr, so I can take it outside. Is this clear? So what I'm going to do, I'm going to go something like nr h cross omega r goes from 1 to 3n. You can also write actually the sum is over nr, whatever. And then this part is what? This part is, you know, this part is going to be equal to V0 plus half h cross omega r. This is fine. Is this clear? And this is actually 0-point energy, this one, no?
Yes, sir.
Physically, what is this? This thing, can anyone tell me? So basically what you see that whatever this is, this part is independent of quantum number. No? This is for sure, no? This has nothing to do with the quantum number. It's independent of quantum number. Can you see that? So basically I can see that this is actually a reference state, I can say. And with respect to that, you have this correction, which depends on the quantum number. It's like a constant. It's an independent of quantum number. So basically, if I go to very, very low temperature, what do you expect? I would expect what? Tell me.
Most oscillators to be in NR equal to 0.
So then what will happen? So I'll have only this term, no?
Yes.
Basically, actually at very low temperature, that will be the contribution to energy. So at any finite temperature, I can measure energy, how it deviates from its low temperature, zero temperature value, just by setting this as the reference. This could be our reference. So in other words, if I write like this, tell me whether this is fine. This one, eta, I can call it as the binding energy per atom, because you have eta times n in the solid at absolute zero. Is this clear?
Yes.
I just put minus just because I want to see this is down. That it doesn't matter whether it's minus or plus. Okay. But this is the convention. I just put like I put minus n eta. Is this clear to everyone? So just think of you're lowering the temperature. When you are approaching absolute zero, all the atoms will have only 0-point energy, isn't it?
Yes, sir.
So if I multiply with number of atoms times 0-point energy, I should get this. Of course, I can also have some V0 also. On top of that, you can have some V0, some reference. But you can also take that V0 to be 0. Okay? Is this clear?
Yes, sir.
So this part gives you this eta is actually binding energy per atom in the solid state at absolute zero. Okay. So now I have the energy expression. So if you have the energy expression, can you calculate the partition function? Yes? How do you
Yes, sir.
calculate the partition function? Canonical partition function in this case. What is the expression? Tell me. Will I write? Kailash, can you tell me? I am calling it capital Q. What will be the answer, right hand side? There is nothing to mug up. You should be able to write down. What is partition function?
Summation of e raised to minus beta e.
Beta e. Yeah, very good. So I should have some exponential of minus beta. And what is e? E I know is just if you go and check n times eta plus sum over nr. I should write. Is clear? This should be the one. What will be the sum here?
NR.
Here, this is actually n1, n2, like this, no? N3, n, isn't it? This sum is for, so you understand that for each atom you have one quantum number n. For atom number 1 it is n1. For atom number 2 it is n2, like this. For atom number, you understand what I'm saying?
Yes.
Like, frankly speaking, it is not like that. For atom number 1 you have n1, n2, n3, because there will be 3 instead, isn't it? I think that is how it is. The notation,
One
just
for
check.
each mode.
Yeah,
One for each mode, or one
yeah,
for
for
each normal.
each mode, I would say. These are normal modes now. No atom, you're right. I have now normal modes. I'm using the language of normal modes. For each normal mode, I have one quantum number. And n varies from 0 to infinity, you know that. But in, okay. So it varies from n is n, all these n's are integers and vary from 0 to infinity. So is this clear? This is a partition function. How many of you understood this? Very
Yes, sir.
easy.
Yes, sir.
Very easy, because this part, what happened? Okay. This part is your E, isn't it? This part is your E. Is this clear?
Yes.
And you know that partition function is exponential of minus beta E sum over. So what will be the next step? How can you do this sum? So let us do it. So actually you see that the first exponential of minus beta times minus n times eta, this will give you exponential of n beta n eta. But I can take it outside sum, no? And then
Yes.
I'll have sum like n1 n2 n3n of what? Exponential of minus, let me write down, h cross beta I can take outside, no? And then I'll have, sorry, I'll have what is inside, n1 omega 1 plus n2 omega 2 n3n omega 3n. It's fine.
Yes.
It's not very difficult, no? Kailash, can you follow?
Yes, sir.
Others are following, I hope. So this is your partition function. Now what will be the next step? Next step is very easy. I have exponential of beta n eta,
Product.
and but you have exponential, which makes your life very easy. You have product for n1 going from 0 to infinity. Isn't it? Then I have n2 going from 0 to infinity. How many such products are there?
N.
3n.
So let me write down the last term. These are like all normal modes of vibration. You understand, no?
Yes.
Very good. And you know how to calculate this? This you have done in harmonic oscillator problem. Each one is 1
1 by
minus
1 minus x
exponential of
minus
minus.
beta.
First one is like this. Second one is going to be what is the last one? Okay, is this clear?
Yes.
Yes, sir.
And then I take a log of q. This will give me, I'm just writing, okay? Because we have done this so many times, isn't it?
Yes, sir.
Very similar. So what will, this is your expression you have. Okay, this is clear.
Yes, sir.
Now if I have a situation, if normal mode frequencies are closely spaced, what will happen?
We can integrate over.
Yeah. Then I can integrate, and but before I integrate, I have to multiply this with what? I have to multiply it with this number of normal modes. We have to multiply this with density of states. So it will be something like ln q, which I'll do in the next slide. So what I'm going to do, I'm going to write now ln q is equal to whatever. Now I integrate over all possible values of omega, but I cannot give equal importance to all the omegas. So I have to multiply it with something like sigma omega, which is actually your density of state. Okay, is this clear? Is this clear? Just so basically I can say that sigma omega d omega, this one, is actually the number of, let me write down, number of normal modes with angular frequency in the range so the idea is that not all the omegas are not all the normal modes are, some normal modes have higher frequency, some normal modes have lower frequency. Okay, so number of normal modes with angular frequency between omega and omega plus d omega is not constant. That is the whole thing. You understand what I'm saying? In the whole, it is not constant. So I have to find a mean. So I have to find a way to, I have to find a way to calculate this sigma omega. A knowledge is required. Okay, because if you have the knowledge of sigma omega, then actually I can, in principle, I can calculate your ln of q. And if I can calculate ln of q, I can calculate the internal energy. Is this clear?
Yes.
So let us calculate the internal energy first. What should I do? Minus,
Derivate with respect.
Del by del bit of ln q.
this is easy to do, no? So what will be the answer on your, so you know this is minus n eta, and you have minus, no? This minus will become plus, and now I have to differentiate this. The argument comes down, no? This is a log. Okay, of course you have this sigma omega d omega. What about this? This is
H cut
Minus
0
beta.
minus minus. Now you differentiate to beta. So you'll take minus and minus will combine plus, isn't it? It will be h cross beta
Omega.
exponential of minus beta h cross omega. I hope I have not
H
done
plus
anything.
omega.
Huh? Yes.
Not beta but omega.
Yeah, sorry, you're right. So this is how it is. Okay. So if I write it very clearly, n eta plus You have h cross omega, and I multiplied numerator and numerator by exponential of plus beta h cross omega. Okay, this will give you exponential of beta h cross omega minus 1, and this will cancel, and you'll have sigma omega t omega. Is fine? Though I have written it here,
Yes, sir.
Yes,
Yes,
sir.
sir.
is this fine? I'll need this. Next thing, what I should do, you know this. Now, since you are doing this course halfway through, I will calculate heat capacity. What is the formula for heat capacity?
Debye.
Debye by del T.
But this one you can also write it as minus 1 by kb t square. I hope this is fine, na?
Yes, sir.
Is this clear what I have written? How many of you can follow this?
Yes, sir.
Yes, sir.
It's fine, na? And this is actually equal to minus kb beta square into it's clear. So your CV is going to be minus kb beta square. Now I have to differentiate again this guy with respect to beta. What I'm going to get? 0 plus, I'm going to do, no, the integration, let it be like this. It will be like this. It will be like this. Just recalling again, I have done it so many times that people also ask me, sir, how do you do this? You know, what is the formula? Tell me, what is the formula?
D f prime minus f d prime.
This is how it is, isn't it? This is fine, Anish?
Yes.
This is fine, na? So what should I have? Iska square of this, isn't it?
Yes.
Whole square. What is the first term? First term is going to be derivative of f. Now f is what? F is 1 actually, isn't it?
Yes.
It is 0. Minus derivative of this guy. It will be what? With respect to
First,
beta, it will be h cross omega. I think this is how it is, isn't it? Because 1 is 0. Huh?
yes.
Just tell me whether I have done anything wrong. I don't think I have done anything wrong.
Sir, multiplied by h omega also. Okay, okay, it is better.
Yeah, h cross omega I have written here. Okay, so I have, if I put it like this, I have kb. Now this minus I take it inside. This minus will be plus. Okay. How many h cross omega are there? H cross omega, h cross omega, h cross omega whole square. But beta square is also there, isn't it? So it is beta h cross omega whole square. Is it clear?
Yes.
Yes, sir.
Of course, you have sigma omega. You have exponential of beta h cross omega d omega, and what is the denominator? You have so what I have here now, these two expressions, and they are very useful. Why they are useful? Because if you give me sigma omega, I'll be able to calculate internal energy and heat capacity at constant volume. Is this clear? What do you need here? Anish, Kailash, Pooja, all Nashit, huh?
Yes, sir.
Whoever is there, Ramanand.
Yes,
Density
sir.
of state.
So once we know sigma omega, this one, then I should be able to calculate what?
Heat capacity.
Heat
Heat
capacity,
capacity.
internal energy, all these things, no? How many quantity? So now, what happened? Anyway, just okay. So if you give me a prescription to calculate sigma omega, then actually I can calculate heat capacity. As simple as that. But general statement, let us see some general statement. One general statement is this. Here, one general statement is as follows. I just look at it. If T is large, what will happen? T large means beta is small. What will happen? Can you tell me? See, then in that case, CV is going to be, look at it, KB. You have beta is small means I can write it like this. Also, I
Yes.
can do the same thing here in the denominator. What is the answer? Look at carefully. CV equals to KB. Now this one you can also neglect. This one, one and one cancel. Beta h cross omega whole square, beta h cross omega will cancel. You have what is sigma omega d omega? Sigma omega is the number of, remember, number of normal modes with frequency omega and d omega. How many normal modes are there? 3n, no?
3n.
So if I integrate this, I should get what? What should I get? I have kb and I get 3n. 3n kb. What is this? This is your Dulong and Petit's law, isn't it? This is done, no? This is done in your class 12 maybe. Dulong Petit? I don't know. Nowadays they do it in class 12. Is this clear? What I've done so far? So the high temperature limit is achieved, isn't it? I hope we are following.
Yes, sir.
Yes, sir.
So actually nowadays what happens that people do quantum chemical calculation, quantum mechanical calculation and calculate sigma omega. But long back it was Peter Debye who came up with a very good prescription to calculate sigma omega analytically. And what he did, he actually he said, okay, for the timing, if I can neglect the discreteness of the solid and I can treat or I can take the solid as a continuous wave, elastic medium, elastic wave, then I can do this. I can come up with an expression for sigma omega. So it's a Debye. Peter Debye, okay? So the idea is as follows. He said the solid, the one I'm dealing with, actually n atoms, okay? We can just neglect this by neglecting the discreteness of the atoms and treating the latter as if it were a continuous elastic. Isotropic elastic okay. How many of you knew this? How many of you heard about the Debye's treatment of heat capacity of solid for heat capacity of solid? How many of you? Answers? I don't know whether you guys know. So do you get the statement? So now go back to solid. Each lattice has an atom sitting there, isn't it? They're vibrating. But for the timing, if I can neglect the discreteness of the atoms, and then I describe this lattice as a continuous elastic medium. What does it mean? So for example, I can think of, see, if small a is something like some average mean interatomic separation in solid. This is of course in the order of angstrom. Okay, so mean interatomic separation in solid. And it's solid, you take KCl, NaCl. Okay, and then I am describing this lattice with an elastic medium. So the elastic medium will have what is that called? It will be, the elastic medium will be characterized by an wavelength. It's characterized by an wavelength. Not an, by a wavelength. By a wavelength. What is this wavelength? Lambda. Okay. Now, if you have a case, if your lambda is much greater than a, what will happen? So let me give you the picture. So these are atoms. And this is the separation A, mean separation. Okay, is this clear? And I can think of a wave. Say for example, this wave is the wavelength is like this. This is your lambda.
Yes.
And this is much greater than your interatomic separation, mean interatomic separation.
Lambda by 2 technically. Yes.
No, lambda by 2. It is much. This is the normal mode. So if you go to harmonic oscillator 0, n equal to 1 level, what is the normal mode? This is a normal mode, no? I can also have another normal mode like this. In this case, this is your, what is the wavelength? You understand what I'm saying? You can go to higher and higher energy and lower lambda. You okay? You understand?
Yes,
As
yes.
your frequency increases, your lambda decreases. But what I'm saying, that as long as your lambda is greater than your interatomic separation, this discreteness does not matter. But what is this lambda? So I can think of these atoms. They're vibrating collectively. I can think of
Mean free path. Lambda is the mean.
not mean free path actually. This is the elastic medium. So there is no mean free path. Okay, this is elastic medium. So actually I can think that okay, I have a situation that this atom is there, but this atom from this position it moved to here. This atom from this position moved to here. This atom from this position moved to here. This atom from this one moved to here, and this one remains the same. So I have a collective movement of the atoms. As a result, in the solid, I have something like an elastic wave, which is of wavelength lambda. Is this clear? This is very qualitative and hand-wavy way of explaining things, but this is how it is. They're collective oscillations. Each atom can oscillate, but they can also oscillate or vibrate collectively. And these collective oscillations would have some wavelength. And there could be different types of collective oscillation. You understand what I'm saying? This is one. Another type of collective oscillation would be something like this. You understand what I'm saying? This one. So these all are actually what? These all are the vibration of this elastic medium, but this is a result of collective oscillation of these atoms. Okay, these are actually called phonons. How many of you have heard about phonons?
Yes, sir.
So basically, so in that, this is a good limit, because in this case, this normal modes of vibrations, this normal modes of vibration of the solid is going to be very similar to this vibration of this elastic medium, and this is where your Debye approximation will be is good. But if I have a situation where is your lambda is in the order of a, what will happen? So discreteness will become important, isn't it? Is this clear?
Sir, can you define phonon again?
Yeah, phonon, I am saying that this is like a collective oscillations. All these vibrations, they're vibrating. The collective oscillation of these atoms. They are collectively oscillating, and there will be many modes of such collective oscillations, and each mode is like a phonon mode. So each mode is like an elastic wave. So you have gone to stadium, now you have seen this elastic, they create elastic wave in the stadium, you remember? Yes, even the human chain can create oscillation in the, this is called, what is that called?
Mexican wave.
Mexican wave. You remember this Mexican wave in the stadium, football stadium or any other stadium? How it is done? So each human being is like an atom, isn't it? But they have some understanding between, we have some understanding, and as a result we can create collective oscillation, collective vibration. They stand up, no? It is just like that. It is like Mexican wave. Can you see? And
Yes,
this
sir.
is a phonon mode, but you can have different types of phonon modes. It is like if you take harmonic oscillation, sorry, particle in a box. N equal to 1 is this, n equal to 2 is this. You remember this in quantum mechanics, particle in a box. So like particle in a box, you can create phonon modes of different lambdas. As you go higher in energy, your lambda goes down. Is this clear, Anish?
Yes, sir.
So these are like phonon modes. These are like phonon modes. What are you doing here? But you're describing the solid as an elastic continuum. You're describing the solid as an elastic continuum. Is this clear? But what happens when your lambda is very small? You have very small, then this is not a good approximation. You understand? If you go to a small lambda, you want to approximate the solid as an elastic medium, then it is not a good approximation. Because in small lambda means what? Your separation is this. A small lambda means this, like this. Then I have a problem, because this is your separation A. A is comparable to lambda or even less than lambda. Then I have problem. When it becomes comparable to lambda, then the vibration of the solid, the frequency of vibration of the solid, or the lambda of the solid will not match with the lambda of that elastic medium which we are assuming. You understand what I'm saying? Let me repeat. You're approximating or you're assuming that, okay, let us treat this solid as an elastic medium. This is a good approximation whenever you're dealing with elastic medium with wavelength which is much greater than the interatomic separation of the solid. When you are in the range, when lambda is close to A, then this is not a good approximation, because then the solid vibrations and the lambda for solid vibrations will not match with the lambda, because solid vibrations are collective vibrations. Okay, they will not match with this lambda. So only when your lambda is large, then you have a good approximation.
So, sir, the phonons are defined when lambdas are large, larger than the A.
Yes,
Is
yes,
it?
yes, it is. It is. It is. So we are not going to talk much about phonon in this course, but it is like that. Actually, if you go very very discrete, then you have a problem with phonons. Okay. So this is so solid is treated as isotropic elastic continuous medium. Basically, actually, all this displacement you can describe with some vector like this. Now, u r of t. You remember, no? That is how you describe a string. Describe a string. And also you have a relation that your omega is you. How many of you know this? That this is velocity of sound times the momentum vector. This velocity of sound. You know this. This is a dispersion relation. How many of you know this velocity? This is dispersion relation. I think everybody knows, but they don't realize that they don't know. They know. This is the velocity of sound because when these modes propagate in the medium, they propagate how? They propagate with the velocity of sound. You know how sound propagates in a medium. What happens? If it propagates in air, some particles vibrate here, that vibration is transformed, isn't it? To the next particle, like this, a collective, isn't it? Anish, this is how
Yes, sir.
sound propagates in a medium. So essentially, it is a sound propagation in solid. So phonon are modes. So by this phonon are collective oscillations, and these oscillations, this disturbance in the medium, they propagate with the velocity of sound. So it's a sound wave with wave vector. This kappa is a wave vector. Okay, this kappa is a wave vector. Can you follow? This is kappa is wave vector. So now can you tell me what will be the sigma? This we should be able to do it now. So let me do it. Your sigma, I am calling it C. C for your continuous elastic medium, sigma C d omega. And if you do this, you will see that this will be 3 times V some volume, twice pi cube, 4 pi kappa square d kappa. Can you can you see a similarity between this expression and something done few classes back?
G of epsilon d epsilon, the
Yes.
particular number is velocity of
It is
stress.
essentially like that. So you can just think of it is essentially like that. And of course, and if I put my expression for CS, this is going to be, but there is a difference here. The difference is the factor of 3, I think, no? This factor comes from, can you tell me why this factor?
Isotropic in three directions.
No, there are 3 possible polarization, no, of this wave. You remember? 2 are, tell me, 2 transverse, 1 longitudinal. Go back to class 12 sound wave. Remember this?
Yes, sir.
So essentially, it's like that. For each wave vector, you have like 3 polarization. So this is the expression for sigma. So this is going to be, I'm calling it sigma omega d omega. So what we did, we took solid, what divided as an elastic medium, and I say that they have collective oscillation. This is like phonons, and this collective oscillation they propagate in the medium with the velocity of sound. Is this clear? So basically, there is a wave equation for this. All these waves they propagate, no, and this propagation is with a velocity of sound. So basically, what will be the Debye approximation? So the Debye approximation is as follows. Debye expression is, I'm calling it sigma d. This is equal to sigma c, the one you have written. When you have lambda is large, so basically there will be a threshold omega below that threshold omega, and this is 0 if your omega is larger than this. Okay, so if I plot this, you will see that it will be something like, here it has omega square behavior, you'll see, and then suddenly it becomes 0 at omega d. So this is your Debye frequency spectrum, the one I've written here. Is this clear? So if I now integrate this, what I'm going to get? What is the answer? Kailash. If I integrate this, what I'm going to get?
0 to omega d, I guess.
Yeah, but of course.
Then
So
0.
I don't need this. It should be omega d, no?
Yes.
So what will be the answer? Whatever, doesn't matter, but it will be equal to 3n, no?
Yes.
Total number of modes. So if I do this in total number of modes, essentially what I have here is 3v by twice pi square cs cube 0 to omega d omega square d omega is equal to 3n. This is what exactly you have, isn't it? So this one gives you 3v this will give you omega cube by 3, isn't it? So now I can always calculate omega d from here. What is omega d? Can anyone tell me what is omega d? This will be 6 pi square n by v whole to the power 1/3, no, into cs. Is this clear? Have I done anything wrong? Just check. I hope I have not. This is your omega d, Debye frequency. This is called Debye frequency. The maximum frequency allowed by this model. I think this is fine, no? Anish, can you check this expression? I think it is fine. Can you tell me what is the value of this? Here I'll do that. If you calculate omega d, how do you calculate omega d? What is CS? CS is, I'm giving you the value. CS is 5 × 10 to the power 5 centimeter per second. Okay. And actually, if I calculate what is known as mean separation, which is V by N whole to the power 1/3, this is mean separation. It is 1 angstrom, which is 10 to the power minus 8 centimeter. If you plot this here, you'll get omega d as 14 second inverse. This is fine. V by N volume divided by number of particle whole to the 1/3. That gives you mean separation, isn't it? Because the cube of that will give you the volume per particle.
Sir, won't it be dependent on the type of solid that we are using?
Yeah,
And
of course, because each solid would have a different velocity of sound propagation will be different. Okay. And also this is going to be different number of particles per unit volume, isn't it?
Yes, sir.
This number of particles per unit volume different for different solid. Okay, so if you calculate, it is going to be 10 to the minus plus 14 second inverse. What is this? This is actually infrared. You can calculate, check. So basically this frequency is in the infrared spectrum. Okay, is this clear so far?
Yes, sir.
Yeah,
Yes, sir.
I have some time, but I'll do that because it is better I do it today. Okay, now if I calculate CV, let me write down KB. You remember the expression? It has expression like 0 to infinity. Now it has become 0 to omega
Omega.
d. Okay, you had this expression. If you go and check, you'll see that you had this. You had this in CV. I can just go and show you somewhere.
Yes, sir.
It is this one. But now I am replacing sigma omega. If you replace sigma omega, I'll have some constant. And let me write down 3by. So don't worry, I don't expect you to remember all these things. Don't need to mug up anything. Okay, this is fine. If I put like this, is this fine?
Yes, sir.
Um, just a minute. Yeah. So this is how it should be. So let us call X as beta h cross omega. Then omega is X by beta h cross. D omega is dx by beta h cross. So then this expression becomes kb 0 to omega d would become 0 to omega d you can put, but since I have changed, so it is going to be something like, because this is the expression beta h cross omega d, because now it is over x, e to the power of x by e to the power of x minus 1 whole square. What is this? X square. This one is x square, no? See, this is x square. This is x square. This is fine.
Yes.
But
Yes.
then I have also this constant terms. Let us club them together. This is a problem actually. If I write too much, then yeah, this will be 3v by pi square cs cube I have. In omega square d omega will become what? X square
Yes.
by beta h cross whole square, then dx beta h cross. So you'll have one thing like 1 over, so I can see that 1 over, this will be there, no? This is fine. I hope this is fine. So
Yes, sir.
if I take this out, kb 3v twice pi square cs beta h cross whole cube 0 to beta h cross omega d, and you have exponential of x to the power of 4 exponential of x minus 1 whole square dx. Okay, is this clear? Now you remember v. What is v? How do you calculate v? Now you can calculate v, because if I go back and I show you this expression, that from here also I can calculate v, no? From here, if I take the cube of this, I can calculate v, isn't it? So actually your v is, if you go and check, it is nothing but 3n twice pi square cs cube by omega d cube. Remember, now this is how it is. V is like this. Essentially, I'm using this expression. The 6 pi square, you can see omega d cube in divided by cs cube equal to 6 pi square n by v, and then you can calculate v from there, isn't it? This is going to be this if you go and check. And actually the final expression, like I can This is how V is. So if you put V here, what I'm going to get in CV? KB 3 into 6 pi square n Cs by omega d whole cube divided by twice pi square Cs beta h cross cube Is this clear? Can I make it little simpler? Pi square and pi square will cancel, no? Can I do that? Pi square will cancel, isn't it? So what I'm get 3n, like 3n kb I can write like this. And then I'll have one more 3 because this will give me 3. I'll have one more 3. Can you see that? And then you'll have 3 by the beta h cross omega d whole cube. The CS cube will cancel, isn't it? CS cube will cancel. But then I'll left with what? I'll left with this integral and this integral I'm going to call it something. The whole thing here, huh? This one I'm calling it, it's called Debye function. This is Debye function fd of Debye function, okay? So essentially I'm going to write that CV is equal to 3n kb into fd of theta d by t, where theta d is, again you know what is this? This is called Debye temperature. Then you can guess what is this. CV is this. So now can you tell me what will happen to this at high temperature? I'll just do high temperature only today. T is very large, no? Like T goes to infinity. What will happen? Just look at it very carefully because you remember what is X. X is what?
H cross omega.
So X is small, so you can expand this. Again, this will, if you expand this, what I'm going to get? I'm going to get, so let me do it here. You get 3 by beta h cross omega d whole cube is there. So this is in the limit when t goes to 0. Sorry, t goes to infinity. Beta goes to 0. So you'll get x4 1 plus x. What is there in down? 1 plus x minus 1 whole square. What will happen? Look at it very carefully.
X4 and x square will cancel.
Whole cube. But this x you can neglect, no? What I'm saying?
X.
Yeah. So this x you can neglect. So you have x4 divided by x square. Can you see that?
Yes, sir.
And what is this answer? You know, the x square means x cube by 3. 3 will cancel. Once you plot, this is equal to 1. Put the limit, it is equal to 1. Can you see that?
Yes, sir.
It's not very difficult. So what happened at high temperature, your CV equals to 3n kb. Because fd, if I have argument like y, as y, your high temperature means, yeah, your y goes to 0. high temperature means y goes to 0, then FD equal to 1. And this is what is this? This is your Dulong and Petty's law. Again, so we'll stop here today. Tomorrow I'll send you the model answer, and individual I'll email, or the TA will email you the corrected answer script. Okay. So I think enough for today. We'll start from here. Almost done with heat capacity. So please read this from the book by Rife, Statistical Physics. Please read the book by Rife, Statistical and Thermal Physics. Fundamentals of Statistical and Thermal Physics. Okay, for this part. Okay, thank you very much for your attention. So now I will
Thank you,
stop
sir.
presenting, and I'm also going to stop recording.